formula for voltage drop calculation is voltage drop equals K times I times L divided by Cm. In this formula, K represents the conductor resistivity, I is the current in amps, L is the length of the conductor in feet, and Cm is the circular mils of the conductor. For a copper conductor with a current less than 50% of its conductor ampacity, the K value is 10.37. The reference for this information is IEEE Std 835.1994, IEEE recommended practice for calculating short-circuit currents in industrial and commercial power systems. Let's delve deeper into each component of the voltage drop formula to understand its significance. The K value, as mentioned earlier, represents the conductor's resistivity. Resistivity is a material property that quantifies how strongly a material opposes the flow of electric current. A higher resistivity indicates a greater opposition to current flow, resulting in a larger voltage drop for a given current and conductor length. Copper is a commonly used conductor material due to its relatively low resistivity. The value of 10.37 for K is specific to copper conductors under the specified condition of current being less than 50% of the conductor's ampacity. Ampacity refers to the maximum current a conductor can carry continuously without exceeding its temperature rating. When a conductor operates at a current significantly below its ampacity, its temperature rise is minimized and its resistivity remains relatively constant. However, at high currents, the conductor's temperature increases, which in turn affects its resistivity. The IEEE standard provides guidance on resistivity values for various conductor materials and operating conditions. Next, let's consider the current, denoted by I in the formula. Current is the rate of flow of electric charge, measured in amps. The higher the current flowing through a conductor, the greater the voltage drop across it. This is because the conductor offers some resistance to the current flow, and this resistance causes a voltage drop proportional to the current. The length of the conductor, represented by L, also plays a crucial role in voltage drop. A longer conductor will have a greater resistance, leading to a larger voltage drop for a given current. This is because the electrons carrying the current have to travel a longer distance through the conductor, encountering more obstacles along the way. Finally, the circular mils of the conductor, denoted by Cm, is a measure of the conductor's cross-sectional area. A larger cross-sectional area means that the conductor has a lower resistance, which reduces the voltage drop. Circular mils is a unit of area specifically used for round conductors. It is defined as the area of a circle whose diameter is 1 mil, where 1 mil is equal to 1/1000th of an inch. The formula for calculating the circular mils of a conductor is Cm equals the diameter of the conductor in mils squared. To effectively apply the voltage drop formula, it is essential to use consistent units. The length should be in feet, the current in amps, and the conductor size in circular mils. The K value should be the appropriate resistivity value for the conductor material and operating conditions. The voltage drop calculated using this formula will be in volts. It's important to note that excessive voltage drop can have detrimental effects on electrical equipment. Insufficient voltage can cause motors to overheat and operate inefficiently, lighting to dim, and electronic devices to malfunction. Therefore, it is crucial to calculate voltage drop accurately and ensure that it remains within acceptable limits. Electrical codes and standards typically specify maximum allowable voltage drops for various types of circuits. For example, the National Electrical Code, or NEC, recommends a maximum voltage drop of 3% for branch circuits and 5% for feeders plus branch circuits. These limits are intended to protect equipment and ensure proper system performance. To mitigate voltage drop, several strategies can be employed. Firstly, increasing the conductor size reduces the resistance and lowers the voltage drop. Secondly, shortening the conductor length minimizes the overall resistance. Thirdly, using a conductor material with lower resistivity, such as copper instead of aluminum, can also reduce voltage drop. Finally, ensuring that the load is properly balanced across different circuits can prevent excessive current flow in any one conductor. When performing voltage drop calculations, it is important to consider the specific characteristics of the electrical system. This includes the type of conductor, the operating temperature, the load current, and the conductor length. The IEEE standard provides valuable guidance on selecting appropriate K values and calculating voltage drop under various conditions. In summary, the voltage drop formula provides a simple yet powerful tool for analyzing and mitigating voltage drop in electrical systems. By understanding the significance of each component of the formula, engineers and electricians can ensure that electrical equipment receives adequate voltage and operates efficiently. The K value, representing conductor resistivity, is a critical parameter that must be selected carefully based on the conductor material and operating conditions. Remember that for copper conductors with current less than 50% of conductor ampacity, the K value is 10.37, as per IEEE Std 835.1994. Voltage drop calculations are essential for ensuring the reliable and efficient operation of electrical systems. By adhering to industry standards and best practices, we can minimize voltage drop and protect electrical equipment from damage.